Section 1.6 is on inverses of functions. And section 1.2, back when we did that, we were told, or we learned, that a function can be represented by a set of ordered pairs. Example I'll use here, consider that a function f of x equals 2x, but I'm only going to use the input of the values 1, 2, 3, and 4. So if I plug those numbers in, if I plug in the number 1 into 2x, I am going to get 2. If I plug in the number 2, I'm going to get 4. If I plug in the number 3, I'm going to get 6. And if I plug in the number 4, I am going to get 8. So I can think of the function f of x, I can think of it as a set of ordered pairs. Those ordered pairs would be 1, 2, 2, 4, 3, 6, and 4, 8. Oops, let's fix that. So this, back from section 1.2, is a valid way of writing a function. So that's the function f of x. Now we're going to introduce the concept of its inverse. The inverse, which we are going to write as f with a little -1 there of x. We're going to read that. That's going to say f inverse of x. What that's going to be is the ordered pairs that result from switching the coordinates. So my new set of ordered pairs is going to be 2, 1 instead of 1, 2. 4, 2. 6, 3. And 8, 4. Okay, that is a way that we can define the inverse. So we have both a function f and f of x, the function, and its inverse, f inverse of x, defined. We can imagine what equation would result in these coordinates. The undoing of 2 times x would be if we were to take the x value and we were to divide by 2. So we can think of it as the inverse function is what would it take to undo the original function, which says to multiply by 2. Well, we know that we undo that by dividing by 2. So you'll see, if I take each of these x values, if I take the 2, I take the 4, I take the 6, I take the 8, and I were to plug it into this new function here, that it would yield the y values that we got. Okay? I'll talk to you in a minute about how to get that algebraically. How do you algebraically arrive at that x divided by 2 function for the inverse? That's going to be a major concept here in section 1.6. But the introduction is basically that an inverse function is the reversal of the ordered pairs. Now, one thing to observe is that the domain, which is the x values, the original function, we had an x value of 1, 2, 3, and 4, and our range was 2, 4, 6, and 8. What you should notice in the inverse function down here is that all of the numbers in the domain down here, which are the 2 that I originally mentioned, the 4, the 6, and the 8, those are the range in the original f of x function. And the range in the inverse function, which is the 1, the 2, the 3, and the 4, that's the domain back in the original function. That relationship will always exist with inverse functions. Okay, so on another page here, informally, what our textbook calls informally, we can find the inverse of a function by just undoing the original function. So for instance, we might be asked to find the inverse of, and I'm going to make up a simple function here. Let's just call it x plus 7. Okay, first of all, it's important to note that is a function. If you were to graph x plus 7, it would pass vertical line test. Each x yields exactly 1y, and so we are talking about a function here. Well, what would it take to undo x plus 7? We're taking the x value and we're adding 7. To cancel that out, the inverse, which we're going to call f inverse of x, is going to be taking x and subtracting 7. Okay, let's test this just to demonstrate that these are, in fact, inverses. So what I'm going to do is a little test here. Okay, I'm going to make a table of values x. I'm going to plug those x's into my original function. And I'm going to plug those same values into my inverse function. Just to keep it simple, we will do 0, 1, and 2. When I plug in 0 into the original function f, that's this guy up here, okay? 0 plus 7 is 7. I put in a 1, 1 plus 7 is 8. And 2 plus 7 is 9. So what that's going to give me is, for the function f, I can think of it as I have the set of ordered pairs 0, 7, 1, 8, and 2, 9. Okay. In the previous definition, I told you that the coordinates should basically reverse themselves. So I'm actually going to make a separate table. I didn't mean to make this the same one. So let me separate this table. And over on the side, for the inverse function, I want to demonstrate that these ordered pairs, oops, I forgot my bracket over here, that these ordered pairs down here are in fact just reversed. So I'm going to take the range 7, 8, and 9, okay, which you can see those are the range down here, 7, 8, and 9, the y values. If I plug those in to this inverse function right here, okay, 7 minus 7, I'm putting the 7 in right here for the x, okay? 7 minus 7 gives me 0, 8 minus 7 gives me 1, 9 minus 7 gives me 2. And so I can think of the inverse function as the set of ordered pairs 7, 0, and I'm reading this right off of the table over here on the right, 8, 1, and 9, 2. So you can see that what I told you up above is holding true. The ordered pairs in the, or I should say the x values, or the domain of the original function, become the range of the inverse, and vice versa. So that is a relationship that will always be true about a function and its inverse. However, we don't always find the inverse this way. We have a systematic way of doing so. And so what I want to do is eventually I want to show you that algebraic way. Before we do that, however, I want to give you a couple of examples where I'm going to give you two functions and I'm going to ask you to verify that they are in fact inverses of one another. Okay, so a verifying type problem, let's go to another page here, might look like this. I'm going to give you, I will say verify that the functions f of x and g of x are inverses. And the functions I'm going to give you here are going to be that f of x is going to be 2x cubed minus 1. And the function g of x is going to be a cubed root of x plus 1 divided by 2. What's going to make this possible is if you look at the bottom of page 63, in the box where they title it the definition of an inverse, let f and g be two functions such that, and they tell us f of g of x is going to equal x and g of f of x is also going to equal x. Okay, this relationship happens, and this is, again, this here is going to be our definition of an inverse. This corresponds with the domain of f being the range of g and vice versa. So this will always happen if you have two functions that are in fact inverses. So to verify this, I'm going to basically do what we did in section 1.5 with these two functions, and I'm going to show that I get the identity x for both of them. That's going to be the key. So the first one we'll look at is what is f of g of x. Well, what that means from section 1.5, it means that we're going to take the function g and we're going to plug it into the function f. So that means we're going to do f of, instead of writing g of x, I'm going to replace that with what that is. Now if I look up on top here, g of x is the cube root of x plus 1 over 2. All right. What I need to do with that now is show what do I get when I take this stuff inside here, the cube root of x plus 1 over 2, and I plug that in here for f. That's what this is going to be. So we'll lower this right to there. F says to take 2 times x cubed. Well, that's 2 times this cube root. Okay, that replaced the x. I have to cube that. And there's still a minus 1 there, so I have to do minus 1. So now I just do algebra. I simplify this. Hopefully when I'm done, I've got x standing there by itself. Well, one thing to note, I'm cubing a cube root. That works out really nice. All that happens is the cube root disappears. So I have 2 times x plus 1 over 2, and I've still got the minus 1 out here. Well, these 2's cancel. I've got x plus 1, and I still have the minus 1, and the plus 1 and minus 1 cancel, and I get x. So far, so good. The first part of the verification has worked. Now I need to show that g of f of x also gives me x. Okay, so same idea. I have to take the function f, and I have to plug it in to g. Well, if I look back up what the function f is, it's 2x cubed minus 1. Okay, so 2x cubed minus 1 has to replace x in the function g. So I look back up on top here at what is g. That's the cube root of all that stuff. So what I'm doing down here, I'm going to do the cube root of, now instead of just writing it as x plus 1 over 2, x has to become this stuff. So 2x cubed minus 1, that's the x. I still have plus 1. I'll show you that up here. Okay. So I got that plus 1. That's what I just wrote down. And all of that stuff is going to get divided by 2. All right, so we'll simplify here and see what we get. So let's do some algebra. In the numerator, I notice that these parentheses are unnecessary, so I'm left with the minus 1 and the plus 1 are going to cancel each other, so I have 2x cubed divided by 2. Suppose I didn't mean all that. Well, you look at that and say, well, the 2's cancel, so I'm left with the cube root of x cubed, and once again, cube roots and cubes cancel each other out, and I'm left with just x. So I have verified that these two functions are inverses. So f of x and g of x are inverses.